Seminario extraordinario. Tenemos de visita desde el jueves a una delegación que viene de la Universidad de Santa Bárbara en California, de la Universidad de Santa Bárbara, no, de la Universidad de California en Santa Bárbara, perdón. Y está aquí con nosotros el doctor Nidzieko y una alumna de licenciatura también de ahí, de la Universidad de Italia, que vinieron aquí como parte de un proyecto que tenemos. Y pues les pedimos que nos dieran un pequeño seminario para que ustedes tuvieran oportunidad también de ver las cosas que se hacen en su laboratorio y lo que también se puede hacer en California, ¿verdad? El doctor Nidzieko es un oceanógrafo físico costero que se enfoca principalmente en los procesos físicos del mar que afectan a los ecosistemas marinos. Él sus estudios de licenciatura fueron en biología marina en la Universidad de California en Los Ángeles. Hizo su maestría y doctorado en mecánica de fluidos ambientales en la Universidad de Stanford, también en California. Hizo una estancia postdoctoral en Woods Hole, en Massachusetts, y trabajó un tiempo en la Universidad de Maryland, en el Centro de Ciencias Ambientales, en Horn Point Laboratory, y desde el 2016 es catedrático de la Universidad de California en Santa Bárbara. Es el investigador principal del laboratorio, que no me acuerdo cómo se llama, pero les dejo a ustedes al doctor. Muchas gracias.
Gracias. Hola, gracias por la oportunidad que presentar una lectura. No hablo mucho español, pero so hopefully this will work. So if you don't speak a lot of English, and also my English isn't very good either, so if you can't follow my English, hopefully the subtitles will help you out here. Does this sound okay for it's okay there? Okay, great. So I'm going to talk today about turbulent dissipation in the coastal ocean, and I hope today what I can teach you or provide you a little bit of the things that I think about along the way. So. And if this gets like off track and is distracting, let me know. We can just cancel it. So. Okay, so I'm from Santa Barbara, where I live in Santa Barbara now. I grew up in San Diego, and the picture of Santa Barbara is here. It's kind of like Seasal, and we're on the ocean. It's a little bit bigger with regards to the campus. We have undergrads and graduate students. And so here's the local ocean for me. This is the Santa Barbara Channel. And Santa Barbara is located on that there where the arrow is. Los Angeles is about 90 miles, 100 miles, or 120 kilometers, 140 kilometers to the east from here. So this is Southern California. And when I take this image, which is an image of a Landsat, a true color image, I take this image and I turn it into, and I accentuate the blue colors. We see things that I'm interested in the coastal ocean. I'm interested in these swirls, the patterns that are created. I'm interested in the fronts that are created in this ocean. And if I take this image and I turn the color bar the other direction, we can see highlights of features on the land. We can see differences in where the environment has been built. We can see places where there's agriculture, like in Oxnard or Ventura, over on the right side of the image. We can see natural spaces. We can see agriculture in the bright green. And the basic thing I'm interested in, going back to this general image, is what are the mechanisms of exchange between the coastal ocean, which I'm thinking of as sort of the intercontinental shelf, this space that's maybe you could out to say 10, 20, 40, 80 meters depth. What are the mechanisms of exchange between this coastal ocean and the open ocean? So what I do as a researcher is I make field measurements and I use remotely sensed data products, or I use remote sensing from satellites and also from drones. And I'll present today some observations from an autonomous underwater vehicle, which is shown here, and we'll talk a little bit more about that as we go. Is this an okay tempo? Is this working? Okay. Sometimes I talk fast, and I don't know how the subtitles are going to go if I get really excited. Okay. I'll try and keep it despacio. So what I'm interested in, I like to think about with regards to a cup of coffee. And what we're interested in is thinking about how different water masses mix. So consider a cup of coffee. You pour the coffee in, and there's hot coffee on the top, and there's cold milk on the bottom, and the hot coffee is less dense than the cold milk, so the milk sinks down. And if we were to think about this as a system from an engineering perspective, here's the midpoint of our system, and then the center of mass is here because there's more dense milk down here, basically more mass at the bottom. When I talk about mixing, the thing I'm interested in the ocean, what I'm referring to is this change in the distribution of a concentration gradient, the irreversible change of where mass, in this case, is located. If we waited for some time, we would see molecular diffusion blur this gradient between the coffee and the milk. And in doing so, the center of mass would be raised slightly. We can think about the coffee with regards to external forces, and we could blow on the coffee because it's tan caliente, and so we have to blow on it to cool it off, but in doing so, we're also imparting a stress on top of that, and imparting a stress to that surface creates a torque, and it moves the coffee around, and it moves the milk around a little bit. Center of mass moves, and when you stop blowing, it sloshes back. And finally, we want to mix the coffee. We want the milk everywhere, so we stir rapidly to homogenize this fluid and make it uniform. And what we're doing in adding energy is we're doing work in the physics sense. We're adding mechanical energy and mixing these two fluids. And in doing so, by the point of doing work is you'll see the blue dot now has raised up to this dashed line. We've increased the potential energy of this through kinetic energy. So this is what I'm interested in the ocean, and my research measures rates of mixing and transport in the coastal ocean. And if that's too jargony for you, you can just think of we're interested in what the spoon of the ocean is. We're interested in what stirs the ocean. And so I think this is the grand challenge that we have before us, is how to better synthesize observations and modeling from different places to create new knowledge to better understand how the ocean works. I'm really excited because I just had a grant that started from the National Science Foundation, as long as it continues to exist, to go to Antarctica in 2027. And we're going to go on the icebreaker, the Nathaniel B. Palmer, which is the big ship in red there. We're going to go to this location here in Antarctica that's called the Bellingshausen Sea. The Amundsen Sea is to the, I guess that's to the west, is a little more better studied. But the Bellingshausen Sea is a little bit understudied, and the Bellingshausen is interesting because it's a location where deep Antarctic bottom water, deep North Atlantic deep water is brought up to the surface for the first time after traveling through the Atlantic Ocean and comes up onto the shelf where it interacts with the glaciers that are there, interacts biogeochemically with organisms that are there. And that water is transformed in some way before it either goes back out into the ocean or proceeds around in the Antarctic coastal current that's there. And so our main motivation in going to this location is to understand what sort of water mass transformations happen, what happens to the water when it comes up and gets close to the coast. And I think about this place that has been visited only a handful of times, well, only in regards to physical oceanography. We don't know a whole lot about it. Compared to other places. I think about this in the context of the Southern California Bight, the picture I just showed you earlier. So before the picture I showed you, here's Santa Barbara. These were the islands. I've rotated it, and the scale here is at the same scale as this image of the Bellingshausen Sea. And here's our cruise track that we're going to take with the Palmer, and we're going to go there once. And we're going to drive along this track just one time. And our goal is to say, oh, here's how this place works. We've been doing this in the Southern California Bight for 75 years. People have been studying the Southern California Bight for 75 years saying, oh, this is how this works. And so it's sort of mind-boggling to me to think about how we can go to a place. What do we need to do to observe this place and understand a little bit about how it works in the context of thinking about another place that we've studied for so long for how challenging it is. And I think about this too, and this is why I'm excited to be here. I'm excited about future collaborations here in the context of the Yucatan Shelf. So here's the exact same size scale. Obviously, you recognize where we are here. No need for a star. And here's our ship track for the Antarctic cruise. It doesn't even go out to the shelf. It's like crazy. So this is the grand challenge. This is why I'm here. These are the questions that I like to think about. And so I hope I can tell you a little bit more about some work that I've been doing in Santa Barbara. So the outline here, I've given you my grand challenge, my big vision of our goal is how can we better synthesize observations? What do we need to do when we go to a place? What do we need to measure? And I think one of the things that we can measure is turbulent dissipation. And I'm going to tell you about that today. And so I'll give you a long background about turbulent dissipation so that hopefully you find something new here. And the point here, if you remember nothing, is that we care about dissipation of turbulent energy because it tells us where the ocean is mixing. It tells us where the spoon is occurring. So I'll give you some background, and then I'll provide you some methods of how we measure dissipation, and then I'll give you some observations. So the motivation here, our focus today is we're going to talk about very high resolution observations of turbulence on the continental shelf. So here's my AUV swimming off of Santa Barbara. The harbor is there to the right. The mountains are behind. It's not as flat as the Yucatan. So this is the turbulent kinetic energy equation. There'll be a quiz later. And you need not care about the details of this equation. The thing to note here is that the u's here represent velocity. And when we multiply u times u, this gives us units of energy, basically. I don't need to focus on the full form of this equation. Just I want to point out that this is the starting point. There's a theoretical, fundamental place to start on this. As we do as physical oceanographers, we'll neglect some terms and just get to the things that we think are important. And the things that are really important most of the time in this turbulent kinetic energy equation are these three terms. The first term on the left we call shear production. And shear production is taking energy from the mean flow. The terms on the right are the fate of this energy. And that goes into terms that we call buoyancy flux and dissipation. And it's this last term on the right, this dissipation, that we're going to talk about today. If you don't prefer equations, you can think about this in a set of words. You can think about this in my coffee cup, that mechanical energy is lost to work, mixing the milk, and heat, which is the dissipation. You rub your hands together and feel them get warm. That's friction. That's dissipation of energy due to heat. So turbulence created by the currents basically rearranges the structure of the ocean or is lost to heat. So this is what we're doing. If you really don't like equations, you can just think of this in terms of emojis. That the spoon is equal to the lifting something up and then viscosity, which the only thing I could come up with viscosity was to put honey and fire together because it's like hot viscosity or something. So it's a bit of a stretch, but you know, that's what we've got here. So we're interested in, we're going to measure the hot honey. We're going to measure dissipation. And the thing about dissipation is it's going to tell us where the spoon is stirring. And this works for us because we have a term that we refer to as mixing efficiency. And mixing efficiency refers to how much energy is used to rearrange the stratification. It talks about how much energy goes into stirring up the milk in the coffee. We can write a formal equation for this that we call the Flux-Richardson number, which is buoyancy over buoyancy plus dissipation. Or if you prefer, it's the weightlifter over weightlifter plus hot honey. And the thing about this efficiency number is that it's relatively constant. It varies some, but the basic thing is that it's a factor of 0.2, give or take, at least amongst friends in a bar. And so we can use this to our advantage because the efficiency is just about always 0.2. Where and how dissipation occurs in the ocean tells us how the ocean is mixing. So the basic idea here is we're going to go out to leading order, we're going to measure dissipation, and we want to use that to think about how the ocean is being stirred. So a recent paper, relatively recent, 2018, which in physical oceanography land is like yesterday. A recent paper from Pearson and Fox-Kemper, they took observations from or results from a numerical model, and they looked at the distributions of dissipation in this numerical model. And what they found was that the sort of at whatever level they aggregated, if they aggregated over the entire domain, which is called global in the bottom right there, or they aggregated in a 30 by 30 degree region, in black, or they aggregated an even smaller 10 by 10 region and looked at the dissipation. The dissipation, again, is shown in the color bars here. So the brighter colors are locations where there's more intense mixing, more intense stirring of the ocean. What they found was that the pattern of mixing, and by pattern, I'm thinking about the probability distribution function, or the histogram of the amount of dissipation, the likelihood of that particular level of dissipation, followed a log normal distribution in this global ocean model. And so that begs the question, as an observationalist, is I want to know, is like, do my observations of turbulent dissipation also have a log normal distribution? How do my observations fit into the things that other things people see? So observations here in the top are from my AUV driving through the ocean off of the Atlantic. And several years ago, I was at a point where I was like, what can I say about my observations in the context of what other people think about their results? And I think going back to our thinking about Antarctica and the Southern California Bight and the Yucatan Shelf, the goal here is to think about, are there perhaps statistical distributions or statistical descriptions that would enable some synthesis across these places? I think this question is even more interesting in the context of this result from Pearson and Fox-Kemper in the context of other papers that have been published. And we're going to dive into the literature here shortly. And the second paper here on the right is from 2021. And in that paper, they said that ocean turbulence, or ocean dissipation rather, was distributed log skew normally, which after you take a log transform, there's this big long tail to the right. So what they suggested is that the log skew normal was a better fit than the log normal for dissipation distributions in the ocean. And we'll go into this log normal business in a second if it's new to you. And their argument was that the sum of many log normal processes, saying, well, okay, well, like Pearson, Fox, Kemper said, like, let's say that stuff is log normal, but if you take a bunch of different log normal things at different levels of energy and you combine them, you're going to get this thing that has a skew to it. And so that was the point of this paper, was sort of advancing our set of observations. And consistent with my idea of like, well, maybe this can be something that we can use to compare different places, they suggested that this distribution, this log skew normal distribution, would be a good way to parameterize dissipation in numerical models. And we run climate models that forecast what the world is going to look like. We run climate or weather models that forecast what the weather is going to do. And all of these turbulent processes are occurring at scales that are below the resolution of that grid. So we have to parameterize the turbulence in these numerical models. Their argument was, well, if we know the statistics of what this turbulence should look like, that might help inform or better inform how we model these processes. So I'm going to give you a little bit of background now. And so to go from 2018 to 2021, we're going to go all the way back to 1967, the kind of one of the foundational papers for this idea of a log normal distribution. And this paper is from Gurvich and Yaglom. And what Gurvich and Yaglom postulated was that distributions of dissipation should be log normal. And their idea was this. So in this picture here, there's a flow from left to right, and it's a sort of classic turbulence picture from an album of fluid motion. And the flow is being illustrated by dye streaks, and the flow is going through a grid. And as the flow goes through a grid, lines that were originally parallel, the flow becomes turbulent. And so you can see this turbulence by the nature of all of the aggregated white areas relative to the black areas. And what Gurvich and Yaglom said was that basically we have to take the energy at this biggest scale, sort of at the scale of these oscillations that are here. And we have to take that energy and we have to break it down to the molecular, or to the viscosity scale. We have to take it down to the scale where the hot honey can have an impact. In doing so, what happens is we break an eddy that is conceptually this big. We break it in half, and we break it in half again. We break it in half, all the way down until we get to the scale at which viscosity can do its thing. And so this process they described as a multiplicative process, that this breakage from going from 1 to 2 to 4 to 8 was the result of multiplication. As you might remember from trigonometry or something, if you take a multiplication hiding down here, If you take multiplication in linear space, if you take a log transform of that, multiplication becomes summation. And so the argument was that if you took observations of turbulence and you log transform them, that then by the central limit theorem, you should end up with normal distributions. So background for the background. When we talk about a log normal distribution, this is a distribution that's normal following a log transformation. So this slide just illustrates this. So these are some data. These are what the data actually look like. And here's a time series of 6,000 points. And if I take these data and I make a histogram out of them, it looks like this. It's hard to see because the data spans several orders of magnitude. So I can make a histogram as well using linear bins. These are the same bins here that are linear, but I could just transform the axis to a log axis. You start to see a shape here, but now the bins aren't equal widths. If we make the bins log width, or equivalently, if we log transform the data, these are the same. Now what we see is the bins are the same width in log space, and you'll see the familiar normal or Gaussian shape that's there. So this is what log normal is that it looks normal, or it has a normal distribution after we do the log transform. And this is what 1967 tells us turbulence should look like. The log skew normal that I told you about from this second paper has a heavy right tail, even in log space. And so here's an example of some data that is skewed to the right. Here's its histogram. And you can see that it has this little tail that's out here. Sometimes you might see this in a probability plot or a QQ plot, where there's a straight line, and this straight line would represent a normal distribution. And then if there's a departure from those lines, that indicates the presence of a longer or shorter tail, which I've annotated here just for convenience sake. So in this example here, there's a long tail to the right, and these points deviate off of this line kind of over to this direction. So back to the literature. It was 1967, and Gerbich and Yaglom said dissipation is log normal. And people went out in the ocean, and the natural thing to do when you have your data, as I do, is you make a plot and say, well, how does this compare to our theory? And so sometimes the observations looked log normal, and sometimes they didn't. And so a lot of the record was people going to different places, doing different studies, and there were only a handful of groups that could do this work. The ability to measure dissipation at this time period in kind of the 80s and 90s was 70s, 80s, and 90s was really focused on a couple of groups that had developed this specific technology. And so they were the purveyors of kind of going out and doing this and then commenting upon it. There's another sort of fundamental paper in 1990 that's from Yamazaki and Lewick that's tried to reconcile this sense of going out into the ocean and finding situations where sometimes it looked log normal and sometimes it didn't. And the basic take home from the paper was that it was okay if you just looked long enough. Or looked hard enough, really. And so here's an example of the data that they had. And what they were doing was they were taking profiles. The profiles here are through the upper 200 meters. And this line in the background is the temperature. So you can see that it's stratified. There's a thermocline up top. Continuous stratification with kind of some stair steps. And then on the bottom here is showing dv dz. So this is the change in horizontal velocity as a function of vertical position. And so anywhere there's really big sort of fuzzy excursions like this, those are locations where there's active turbulence. And what they did was they said, well, if you were to look in this blue box and make a plot of this blue box, it looks kind of like this. This is that property plot, or that QQ plot, where we can see that there's deviations with different tails. Then they said, well, okay, what if you looked here just in a single patch? And then they did some averaging, and lo and behold, if you looked small enough and averaged small enough, then things fell on the one-to-one line. And they were like, well, okay, Gerbich and Yaglom, this theory, this thing we think works. This thing works if you're looking at a small enough scale. And they reasoned that this was because Gerbich and Yaglom, this might be on the next slide. Yeah, they reasoned that if you looked over this really big blue box, you were combining different patches. This violated sort of the laboratory scale assumptions of Gerbich and Yaglom. But if you looked at a really small scale, then things would work out. And so we basically hung on to this idea of log normal after 1990. Let's take one more step back. It's important to understand here that almost all dissipation estimates have an averaging process built in. So what we're doing here, so this is dissipation. This is the thing we care about. And what dissipation is the sum over the all of the tensorial directions of basically velocity, strain, and shear. In practice, what we do is we just measure one or two components of that. In particular, for example, here's an example of du dz. So we measure one component. We measure horizontal fluctuations through the vertical. And then what we do is we take a Fourier transform. And we do this, we take a Fourier transform because the measurement process itself has some noise. And so what we do in taking this Fourier transform, if there was no noise, we could integrate over the entire wave number spectrum, which is equivalent to averaging. The reason we do the Fourier transform is that there tends to be some noise. So we basically integrate over the part of the spectrum that we say, cool, this is good. And then we correct for the part that we've thrown away. And so this is the procedure that we use because of the measurement technique. Okay, so that's where we're at right now. And so the basic thing with, so to sum up some of this background, the heart of this explanation from the 1990s for why the observations didn't match our 1960s theory was a distinction between, on this slide, I have it labeled as internal and external intermittency, because that's the words that they use. You could think of this internal, you could think of this as, this is the rate at which patches break apart. External intermittency is the rate at which the energy level changes. And so in this cartoon, there's one flow state, and then here's a second flow state. This second flow state is calmer than this first flow state. And the level of turbulence is different. And so the idea in graphical form here for what we understand as theory is that the statistics work here, but not across these variable states. And it's the idea that across different cruises, different casts on a cruise, that the energy levels changed, went from one cartoon to the next cartoon. And that's why some of the observations were not log normal. So that's our quick survey of turbulence. That's all there is. There's just like 4 papers. And we're back to the future now. So in 1967, we said it was log normal. Most of the late 1900s, we made observations that said it's log normal, except when it's not. And we found out that it was still log normal because we just had to be looking hard enough. We have modeling observations or modeling results from 2018 that say it's log normal. But then we still have this more recent paper that put things together and said, just admit that there's this long right tail to it. And so that's where I'm at in thinking about my observations. You're totally experts on turbulence now, right? Okay, thanks for hanging with me. So we want to know about how can we synthesize observations across different places. We're measuring dissipation because it tells us where the ocean is mixing. We have some assumption for what we think the dissipation should look like. Now I'm going to tell you how we measure this, and then I'll give you some observations. Oh, okay. So what we use is a Remus 600 autonomous underwater vehicle. This is about 4 meters long. It weighs 270 kilos. And we put into this AUV, we put what's called a Rockland. Rockland is a company that makes these instruments now. So before you had to be an expert and know how to make this, now you can buy this. It's really kind of changed things significantly. So we take this instrument and we shove it into the nose of the AUV. So here's the micro rider, and I'll show you the probes in a minute. We put some other instruments in here for measuring the velocity. And then we go out into the ocean. And what the micro rider does is it holds very sensitive probes for measuring temperature, velocity, and conductivity fluctuations. And importantly here, or the thing we'll be talking about today, are these shear probes, which are located here in the bottom of the picture. And what they measure are velocity fluctuations that are transverse and vertical to the vehicle axis. They measure at 512 hertz. So they measure very fast. And basically, we're looking for, as we move through the water, we're measuring the gradients dv dx and dw dx. And when we want to average these, but in practice, what we do is we do the Fourier transform and we integrate over that wave number space because the measurements are a little noisy. So our data processing removes these, and so this is what we call shear. So we call them shear probes because we're measuring small scale shear. So we take out these shear signals that are coherent with vehicle accelerations, which is another reason to do this Fourier transform. It lets us take out parts of the vehicle, parts of the signal that have the same noise as the vehicle. We take this raw signal, we do a Fourier transform. The orange lines there show the theoretical curves that we fit to recover the parts of the spectrum we can't integrate over, and we end up with a number. We end up with this hot honey dissipation measurement. So I'll finally, after a grand half hour plus, show you some data and try and put this together. So we ran these missions on the continental shelf and the Santa Barbara Channel on 2 dates. So this is just off the harbor here. And what we did was we ran a series of alternating behaviors with the vehicle that alternated between horizontal transects at 3 different depths, at 2 meters, 6 meters, and 10 meters depth. And then after that, we'd do a deep profile so that we could measure the stratification. And we called this the bow tie. I don't know why. So we're going to focus on the surface transects of this bow tie, which is about 2 kilometers offshore of the 50-meter isobath. So you can see here, this is the shoreline located here. Here's the harbor. This is the lines of bathymetry that are here. And the vehicle drove this black path, came out, and spent a lot of time here. You can see the depth profile during this mission. Basically, from this point forward, 20 through 37, the vehicle is going at 10, 6, 2 meters depth, and then it does a profile. We're going to contrast 2 data sets, one with weaker and one with stronger winds. The important thing about this to think about is this time period with weaker winds. So the period of the observations are shown in the light shading here. The wind is here in the red with wind gusts and wind speed. And then this is the tide that we observed. And the main thing to think about here, conceptually as a cartoon, is that here the sea surface is fairly calm. When the wind is strong, of course, as we see out here yesterday, or maybe this afternoon already, when the wind is strong, then the waves break and there's white caps. And it's this, that white capping is creating turbulence, and that turbulence has to be dissipated. Stratification, for those of you that care, is also stronger during the first mission with the weaker winds compared to the period with the stronger winds. These are just profiles through time. The horizontal axis is time, the vertical axis is the depth, and you can compare the relative strength of stratification in blue to the dissipation in orange, visually, and see that there's strong dissipation on this mission, there's strong stratification and weak dissipation on this mission. This is the main take home here. So we have 2 very different days. One is windy and turbulent. The other is not windy and stratified. So here's what I expect based on the introduction. This is where I was at with like, hey, here's what I think I'm going to see. So with weak winds, I thought, well, there's no waves at the surface. There's low intensity turbulence. And so I thought through time, like conditions were all going to kind of look just like so-so. And then I thought with strong winds, like you're going to be driving this AUV through a patch where the waves have broken and then a patch where the waves have not broken. And so you're going to be going through patches of strong turbulence with breaking waves and then kind of background turbulence, breaking waves, background turbulence. And I thought for sure that this was going to lead to a different distribution, that the distribution of this patchy strong turbulence would give us this like skewed thing that one paper saw, and that this kind of calm, quiet condition would be like, here's the average situation. It's a cliffhanger. We'll see if that really comes true. So going back to, again, the final synthesis of this, we want to think of these observations are contained in a numerical model grid cell. So here's our vehicle path. Here's the vehicle path in 3D. What we're doing is we're coming back and measuring lots of stuff at the surface of the ocean. If you want to think about this at kind of the cartoon level, we're trying to characterize what are the statistics, what are the physics in this one little grid cell here. So looking at these distributions, so here are the observations from the strong winds. These are repeat transects every hour or so. The time of the transect is here. The number here represents the hour. You can see the wind speed in this image here. And just for sort of time reference, the symbols here represent where we are in that time period. So all of the data here are combined into histograms over here. If we do a Kolmogorov-Smirnov test for normality, anything that has a triangle on it passes this test for normality. So for these 7 observations that are here, only 2 of them possibly have a log normal distribution. That's the big reveal. So if we start to break this down, if we say, well, this is, you know, we were hoping for some like beautiful alignment with theory, but we don't have that. Maybe we should start to look harder, as suggested by prior papers. And so if we break this down and look at it by individual depth, if we look at 2 meters depth in orange, 6 meters depth in blue, and 10 meters depth in purple, and make individual histograms of those, and study those histograms, and do that Kolmogorov-Smirnov test for normality, we start to see a few more distributions that are perhaps log normal, but by and large, these are not log normal distributions. It's the Journal of Negative Results. So just like the wind event, if we go to the calm conditions, if we look at the calm conditions, we see normal distributions only at smaller spatial scales and in and parsed into these individual depths. So I'll save you the dragging through more observations. And basically, the take home is that none of these distributions, very few of these distributions or observations are actually log normal. Not even close. They're all over the map. And you know, some of these things are 2 meters to 6 meters. They just look totally different. They just have nothing to do with each other. Which on one level is discouraging because you're like, well, I want it to be like theory. On the other hand, you're like, well, maybe here's an opportunity for learning something new. So I was surprised because in aggregate, these results are completely the opposite of what I expected. And we'll come back to these conclusions here in a second. But this is basically all of the observations for the weak conditions. I want to point out that it spans 4 orders of magnitude here. And here are the observations for the strong winds, and they span roughly only 3 orders of magnitude here. Also note that it's a much higher order of magnitude. So they're sort of centered around, say, -6.5, whereas the average here is closer to -8.5. So the strong winds are indeed more turbulent, but the distributions are very different. So let's proceed with a thought experiment. I like to create toy problems when I can't explain something. I like to create something that I know what the answer, or at least I think I know what the answer should be. So I'm going to make a toy problem in MATLAB. I'm going to make up my own data. And what I'm going to find out in making my toy problem and hopefully show you is that stronger turbulence is skewed to the right, but this amount of patchiness relative to the strength of the turbulence alters the distribution. So for my thought experiment, I created a data set of instantaneous shear estimates that are log normally distributed for the ideas of Govertz and Yaglom. And basically, I just used a random number generator. And for that random number generator, I imposed some variability around that random number and then some average level. And so here's my set of random numbers that I generated. And I plot them like a time series. You could think of this as just like the time series I showed you before. And if I take this data, make a histogram, and then log transform it, it is log normal. So here's a log normal distribution in the dashed line. You can see my sample population that's here. And And analogous to what we do in the real world or in our measurements, we average these 512 points to come up with an estimate of dissipation. So the average of these numbers is right here. And so if I do this over and over again, if I repeat this experiment of making up 512 numbers from a normal distribution and then averaging them and then plotting them, this is the result that's here, is I end up with a distribution that has this tail to the right. And actually, this is a known property of the log normal distribution, that when you do this, when you average it, because every now and again, since it's just sort of like a statistics thing, right? If you're a biologist, if you sample this distribution improperly or incompletely, sometimes you sample way out in this tail occasionally, and that handful of samples that are way out here is going to cause this average to shift to the right. And so the fewer observations you grab, the more likely you are to occasionally get a really big number. So what this does is that it leads to data with stronger turbulence to be more heavily skewed. So here's an example of the underlying sample population. Here's what its time series looks like. Here's the histogram of it. And then here's that same data shown in the log or in the QQ plot here. Here's the same exercise, but I'm going to draw my data from, instead of a population that's narrow, I'm going to draw it from a population that is very wide. So these have the same mean. They both have a mean of -7, but the population in the top right has a much wider distribution. And consequently, a time series of this distribution looks a lot noisier than this one. When we average it, it has this distribution, it has this tail to the right, which is what we observed. You can think of this in the strong wind condition. The weak wind condition, we saw something that looks like this. In the strong wind condition, we get this kind of high variability out to the right with this long tail. Next, we're going to create some large-scale patchiness, and think of this as going through breaking waves and non-breaking waves. And so you can think of this as going through different turbulent states. And here, this is illustrated in the histogram just by sliding this histogram back and forth and moving it back and forth, and then averaging that and creating a time series. So counterintuitively, that when we impose this external variance, we move this histogram back and forth and sample from that distribution, it actually reduces the skew. So here's a situation where I don't vary the position of this at all. I just make a time series of it, and it looks like this. Over at the extreme, I'm taking this distribution and moving it back and forth in a sinusoid, like up and down, up and down. And so you can see some of the sinusoid that's here. You can see this sinusoid shape. And then you can see here in the aggregate, actually it's easier to see here in the QQ plot, that basically as we increase and go from being uniformly turbulent to patchy turbulent, you can see that this tail actually gets smaller. And so this was very counterintuitive to me, that basically as we increase this patchiness, we're basically masking the underlying skew that's created through our averaging process. When the turbulence is really weak, this resulting distribution is dominated by the large-scale patchiness. So now you can really clearly see the external signal that I'm imposing over there. That's patchy sinusoidal signal. The distribution looks kind of bimodal, and you can see that it has these really crazy, crazy tails that go way high and way low. So that's my big conclusion. I have other information about this and things that I have to explain this, but we don't have to get into the weeds for that here. So in aggregate, the results here are the opposite of what we expected, that in the weak winds, basically patchiness dominates the distribution. We have this really large distribution with this really long, gentle tail out to the right, because we have lots of background stratification, lots of background turbulence that's suppressed by the stratification. But every now and again, we end up with something that's surprisingly turbulent. And those one or two turbulent patches lead to sort of extending the turbulence, or this distribution out to the right. In contrast, whereas before with the strong winds, I had this picture of, well, we'd be going in and out of waves. In fact, it's not going in and out of waves. It's just like gangbuster turbulence all the time. It's just energetic, lots of dissipation going on, and the variability associated with the waves probably masks some of the tail that's present in all of those smaller distributions. And so this really active turbulence yields something that looks a little bit more like a log normal distribution, but it still has a hint of a tail. So I'll pause there or stop there and take any questions. I want to thank NSF and ONR for funding this, collaborators at the Applied Physics Lab at Washington for helping me with this, and thank you for your patience and attention.
It's a bias that.
Hello?
Okay, so what you're looking is a bias in kind of the measuring technique that give you that different profile, or is complete measuring because of the way we can measure stuff like this?
Yeah, that's the take home. That's part of the take home here, is that when you average, it's going to be skewed no matter what. And so I can't find anywhere that, like, I mean, this is like a known property of the log normal distribution, like how this works, but I can't actually find anything that describes this, which is sort of surprising. But the thing that I didn't go into today is I actually don't believe that this underlying distribution is log normal. Anyways, so I've moved past this, but it makes a good graphic story.
The other thing is, like, your maximum in the low energy measurement that you have of dissipation, you have a consistent large number of measurements at is that your actual measurements?
Yeah. These are the actual. These are real.
Yeah. So that's the between, it's somewhere in between 10 to the minus 9 to 10 to the minus 9.5, where you have like the most number of observations. Is it?
Right.
What's happening there? Any idea?
No, I don't know what's happening there. I think, if we go back to kind of what this looks like. So here's the calm conditions, and these are the observations that we have. It's really strongly stratified. I think that it's just, but it's strongly stratified, but the water's still moving. There's still some wind. There's a little bit of wind. It's not nothing. It's not like, it's not like flat glassy. So there's still a little bit of wind. So there's still just general motion. I think that's what the energy level was. Our noise floor is like, the noise floor is here. So we're an order of magnitude above the noise floor. So I think it's real. But I don't know what the whole deal is. Sorry, say it again. Right. Basically, we're measuring these velocity fluctuations, and these velocity fluctuations, we're measuring the energetic part of the wave number spectrum, and then that has a tail, that, like, the high end of this wave number. Like here, these are low frequency, these are high frequency, and the theoretical spectrum goes off like this, but then like drops down at the Kolmogorov scale. And it's this fitting through the kind of like lower wave number region that makes this work.
¿Alguna otra pregunta? A ver.
Hi, thank you for the presentation. First of all, I'm new here in the program, so I'm not an expert on oceanography, but I was thinking about the mixing processes. as of you are your research is based only on the end member as seawater, or it involves mixing processes of like freshwater, seawater, or is it the mixing process of heat? Was it the mixing process of ions? I didn't understand that part from the beginning.
Sure, yeah.
So, because the dissipation is, well, the effect is the loss of heat, right?
This is all like, you could think of this as entirely like a mechanical energy budget. And we have so this is the turbulent equation. We have another equation that describes the mean flow. And you can take that equation that has a mean flow, and if you do what's called a Reynolds decomposition, you end up with a term that looks like a sink. So in the mean flow, the thing that slows the flow down is viscosity. If we have turbulence, then we also have a term that is turbulence is extracting energy out of the mean flow. So the mean flow can slow down either by viscosity or by turbulence, but the turbulence is much, much bigger. So now when we take that energy and we take it out of the mean flow and we put it into turbulent energy, the over bars here are time averages. So there's some like time scale that's involved in this. That mechanical energy can only go two places. It either goes to rearranging the density, which is your question about freshwater. So if there's freshwater and there's ocean water and there's something that's stirring that, like tides or wind, then it takes work. We're going to lose energy stirring that fresh water into the ocean. Or we have this dissipation. And so at a molecular level, it's going to heat, but it doesn't change the temperature because the heat capacity of water is so large. Mm-hmm. So like with the temperature, the ocean doesn't raise because of dissipation. It's just like the physics explanation of it. You know, if you have a puck going down a incline, it has to overcome friction, and then when it gets down to a flat spot, it stops because of friction. This dissipation is friction.
Okay. The other question that I have is, I didn't quite get the part where you make the clusters based on the depth, because you show us some distributions based on depth, but I wasn't sure if, again, the data shows that asymmetry that you mentioned as a main thing in your research, that one. Yeah. Even when you make those clusters, you're still having this positive asymmetry.
That's exactly the point. Yeah, is the even when we make into smaller segments and look only at 2 meters and only at 6 meters or only at 10 meters, there's still always sort of like stuff out to the right. So that's the point of this plot, is that there's still the tail to the right.
So there's something that is still missing to consider.
Yeah.
That it makes those changes on those points.
Exactly. Yeah.
Those anomalies. Okay.
Trying to understand like how important the tail is relative to the rest of the data.
Okay. Well, those were my doubts. Thank you.
Thank you.
Otra preguntita por ahí.
I have a question or a comment.
Well, I think obviously these studies and these understandings will be of great importance, I think, particularly for numerical modeling, I guess. So can you comment something about all these studies, how they could impact numerical modelers or models that we use nowadays to predict maybe climates or currents? Or
yeah, my outlook on numerical models is, and I think most modelers share this, is the output is only as good as the input. And so I think that we know that there are limitations to numerical models. We know that some of those limitations are related to artifacts like numerical noise, numerical diffusion. And so I think that if we go to something like this, where the end goal here is to say, well, this is the same motion on 2 different days, and obviously the results here are incomplete. If we were to measure this constantly all the time, we would end up with some fuller picture of what this looks like. And then we would be able to know the statistics of that place and say, okay, this is what our answer should be in the numerical model. The numerical model should have statistics that look something like this. I think also relevant to that numerical model perspective is something that I forgot that I was going to say. What was it? It'll come back to me later. Yeah, there's a... Yeah, there's a good reason though, so it's really a good answer.
It's well, the reality is that well, with here again, you can calculate with your shear measurement some sort of diffusivity and viscosity measurement. So that's what, and also you have the dissipation. So this could be compared to our numerical models into the kind of parameterizations that we have into it. But I think the big thing is that the actual parameterizations, like the K epsilon modeling that we use into our regional models, haven't looked back into these in situ data sets of dissipation and energy production to see how we improve that. And I think that's a big thing that eventually somebody will have to get and look at it.
Yeah, I think to that end, I think these 2 distributions were created by different forcing conditions, and so if you're going to draw a conclusion of the way a place works, your simulation has to encompass that range of variability. And so if we can understand what generates these distributions, then we can better understand perhaps the distribution of the forcing functions themselves, of what needs to be captured in a simulation.
Well, I think this is very interesting, right? Because it shows us that well, what I like about your work presentation is that you went back all the way to the theoretical part. Well, that's been going on since maybe 40 years now or 30 years now. And we can still see that we still don't really understand what's going on into that scales of motion. No? We're talking about turbulent microscopic movements, like happening really fast and in really, really small scales, right? But at the end, you end up seeing their effects on bigger scales, which is what we can see with our eyes, I might say, or with the satellites, right?
Yeah, which is the point, actually, as you're speaking, it reminded me of the thing that I was thinking about. Going back to the spoon, it's like we're measuring dissipation because that's where the stirring is happening, and the things that the models don't do very well or don't do as well is deal with scalar properties, particularly salinity. And so, there's a next level of physics that involves, to your question about freshwater, there's a next level of physics in the models in terms of redistributing those scalars that may or may not be correct.
For me, it comes to mind like understanding how there's exchange of properties like between these bodies of water that we have in Yucatan, like inland, like these wetlands, and how they communicate with the open ocean, and how they both exchange turbulence or energy or thermal dissipation or mass dissipation with salt. So I think this is very nice. I like.
Thank you.
No, nada. Bueno, pues muchas gracias, Nick.
Thank
por
you.
tu presentación.